Okay, let's get started. Lepton session. The first speaker is Professor Jeonghyeon Song, and she will talk about the two-Higgs-doublet model in light of the CDF W mass. So please start.
Hello. It's good to see you all here. So, and thank you for your invitation this very intensive mini workshop. So, my title is the two-Higgs-doublet model, and in light of the CDF W boson mass, which is our main topic. And today, I'd like to talk about the muon anomalous magnetic moment also. So, this talk is based on two papers, our recent two papers. So my collaborators are Jeonghyeon, Sujin Lee, and Kingman Chung and Cheating Liu. Actually, Cheating Liu was a research fellow in KIAS also, and Francis Daniel in APCDP. These are my, so let's get started. I think we have heard a lot about this CDF W boson mass. How can I say anomaly? So actually, the real question is how much we can trust it, the result. This is the current status of W boson mass. I think all of you have seen this a lot. So we have D01, 2, Opal, and Aleph. This is Atlas, which has a small uncertainty here, but CDF result has the most significant uncertainty, very precise uncertainty, but the central value is quite different. Yeah. Okay, so this is the result, right? And actually, I'd like to share some figures that impressed me and that excited me. So first one is, actually these figures are from Professor Kotbal's talk last week, right? Last week. Yeah, in KIAS here. So this is the depth chamber alignment. I don't know any details, so don't ask me. But they aligned the depth chamber by using cosmic muon ray. Actually, this number impressed me a lot. 480,000 cosmic muons. So this is the before the alignment. This is the after alignment result of this R delta phi. Don't ask me the detail, but if you look at these two figures, then actually this alignment improves a lot, right? And another thing is this one, tracker calibration. So CDF used J psi and epsilon. They're decaying to 2 muon, right? Then they have a very nice calibration. As I know, right? LHC cannot do this calibration. LHC only adopted the G boson decay calibration. I think this is very good point. Okay. So, and in addition, I'd like to focus on this Aleph measurement of W boson mass. Aleph W boson mass measurement is a little bit different. They used this all data collected at CM energy from 161 to 209 GB. So they did this kind of, how can I say, threshold scan. And if you look at the Aleph central value, that is very consistent with the CDF central value. Of course, the error is huge compared to CDF error, but you know, this can be something. I don't know. You have to do it. Yeah, rigorously. And they can do, because one machine scanned all the energy scale, so they can have, how can I say, coherent systematic uncertainty analysis. I think this is also very important. This is the kind of final summary of the current status of W boson mass. This as far as I know, yeah, their main focus is like CDF or the other. Yeah, Aleph was kind of special. Actually, one of my colleagues, he belonged to Aleph. He said that. Yeah. So we have three important values for W mass. This is the PDG value. I'll tell you what it is. And this is F plus value, and this is CDF value. Okay. So second point is the so-called Peskin-Takeuchi oblique parameters. What is that? Because so if we have something anomalous thing, right? Something anomalous in the W boson mass measurement, then the question is how we parameterize it. And one efficient way is the so-called oblique parameter, which means that it parameterizes the new contribution to the gauge boson self-energies. And for example, if you have a new Higgs bosons, these Higgs bosons, they can contribute to W boson self-energy through this charged Higgs boson, right? This is a pseudo-scalar, and this is the other CP even neutral Higgs bosons. Of course, in the standard model, we set SPU to be 0, right? That's the central value. Then, as I told you, the PDG value of W boson mass is from this global fit to the various electroweak observables. I've listed all the observables, right? And we have 23 observables, and we will allow 7 free parameters. 7 free parameters are like this: Higgs mass, Z mass, and this thing. Then in the standard model, that's it, right? So we have 16 degrees of freedom. Then we can do this global chi-scale analysis. Then if you look at this one, so here PDG 2021 means that they used the W boson mass measurement before CDF value. Then in the standard model, the chi-scale value is, minimum chi-scale value is 18.73. So actually, which corresponds to the p-value of 0.28, 28%. So which is very good. But if you use, instead of the previous W boson mass world average, if we use the CDF value, then chi-scale value becomes 64, which means your p-value is below 0.00001, so 10 to minus 5, which means the standard model is not correct. That's the situation, right? So then we need BSM, right? So then we allow more free parameter. One good way is to allow SPU as free parameters, but in usual, BSM models, the U parameters occurs from dimension 8 operators. So one good way is we just set U equal to 0, and S and T become free parameters. Then now we have 9 free parameters, and we have 14 degrees of freedom. Then if you use CDF W mass, then your p-value becomes 0.22 with this new S and T. We don't know what the new physics model is, but it is accepted. If your new physics model can explain this S and T, that's the story. Yeah. So let's explain it in two-Higgs-doublet model. I think all of you are very familiar with the two-Higgs-doublet model, and we have 2 different Higgs-doublet pairs with vacuum expectation values of V1 and V2. And here in the beginning, they were worried about this tree-level flavor change in neutral current. So they imposed this discrete G2 symmetry to avoid it. And under this G2 symmetry, phi1 becomes phi1. So it doesn't change the sign, but phi2 flips the sign. Then you can write down your scalar potential with the CP invariance. But here, M12 square softly breaks the G2 symmetry. Then what's the situation? Then because we have decided the G2 parity for phi1 and phi2, but we have some freedoms for right-handed fermion singlets, right? Singlet G2 parities. Then we can have 4 different combinations which determines type 1, 2, X, and Y. Then we have 4 types, but in addition, there are 2 scenarios for the standard model like Higgs boson. One is because the standard model Higgs boson is a linear combination of this small h means CP even light neutral Higgs boson and large h, which means CP even heavy Higgs boson, their combination. So actually 125 GeV can be this light Higgs boson mass, or 125 GeV can be this heavy Higgs boson mass. So I call it this normal scenario, and this one is inverted scenario. So in the case of inverted scenario, we have additional light CP even Higgs boson. Yeah, that's the situation. Okay. Okay, then, so I'd like to study the 2-Higgs-doublet model totally, comprehensively. Then I sit down and I considered all possible cases, and we have 16 cases, which means that we have 4 types and 2 scenarios, and we have 2 different W boson mass measurements. So we have considered 16 cases for these 6 parameters. And we didn't assume any assumptions on the masses or coupling. So here you can see 7, but one of this M small h or M large h will be set 125 GeV. That's why we have 6 parameters. So we will impose a series of constraints, but one of the most important one is this theoretical stability, which means at the end, roughly means that our quadratic couplings in scalar potential cannot be too large. For example, I'm sorry. Okay. Oh, some kind of lag. Okay, here. So here I write down the quadratic couplings in terms of mass parameters and tangent beta in the Higgs alignment limit. Then you can see, for example, lambda 1 has this tangent beta square term. So if your tangent beta is like 10, then we have 100 already here, then it'll blow up your quadratic couplings. Then it'll break any, unitarity or perturbativity. So it's not good. So at the end, we will need some kind of mass degeneracy or similarity. That's the situation. But if you combine this theoretical stability with the CDF W boson mass, then an interesting thing happens. So let's see what it is. So this is the allowed parameter plot. Y-axis is delta MA, which means that mass of pseudoscalar minus charged boson mass. X-axis is delta M big H, so big H mass minus charged Higgs boson mass. And left panel is for PDG case, right panel is for CDF case. Okay. So here, red and yellow, they are allowed parameter space by S and P measurement. Then, okay, what's wrong? And okay, this looks very familiar. And at 2-loop level, you can see the exact mass degeneracy between big H charged Higgs boson and pseudoscalar mass. This is well known. But if you apply the theoretical stability, for example, let's take lambda 3, which has no tangent beta dependence. Then this, how can I say, light blue area is for this absolute value of lambda 3 to be less than 4 pi. So this is kind of an upper bound of perturbativity, right? Then you can see some kind of an overlap, right? So, okay, my mass degeneracy is not that big. I'm sorry, I forgot to say, we considered very heavy charged Higgs boson mass, 1.5 TeV, okay? Then, okay, but if you impose the value of lambda 3, absolute value of lambda 3, to be less than 1. This is very crucial for the RG evolution later. Then that's this green band. Then you have some kind of overlap with PDG W boson mass. That's good. But look at the right panel. Then actually this ST parameter, allowed parameter point is this, bands. So this exact mass degeneracy is excluded if you accept the CDF W boson mass. But the same thing happens. But if you require lambda 3 less than 1, then there's no overlap for charged Higgs boson mass equal to 1.5 TeV. So as you will see, very heavy masses are excluded. Okay, this is one of the best, obvious before. Yeah. Red is 1 sigma, yellow is 2 sigma. Okay. So here, mass parameter. I'll explain it. Yeah, but here, this is kind of illustration. So we will do all the scan. Yeah, all the scan, okay? So we did the random scan without any assumption, okay? Without any assumption. So we run over the parameter like this. So this is a normal scenario. So big H is heavier than 125, something like that. And in the inverted scenario, this small h should be lighter than 125. That's why we have this range from 15 to 125. But I'm so behind, so I'll be quick. So we took 4 different steps. The first one is theory plus flavor changing neutral current constraint. Second is this is STU parameter. And third, I think this is, we were the first to study this RG analysis for this CDF W boson mass. So we require that this model's cutoff scale should be larger than 1 TeV, at least, right? And the final is the Higgs precision data and Higgs bound. So this is the theory and flavor change in neutral current, but I actually don't bother about the details. The final point is that this one. So your quadricoupling should not be too large. That's the point. And this efficiency is this, usually, this is a very nice review of this two-Higgs-doublet model efficiency constraint. So you can see all kinds of constraints, but those constraints are different for type 1X and type 2 and Y for the charged Higgs boson mass. If you look at this charged Higgs boson mass, then there exists the lower bound, like 580 GeV. But if you accept the most recent NN error calculation, the charged Higgs boson mass lower bound goes up to 800. But for this work, we took the conservative stance, so we took this 580 GeV lower bound. And actually, let's get into it. So let's see the allowed region after step 1, which means that just theory and flavor changing neutral current, no W boson mass whatsoever. Then you can see the upper panels are for the normal scenario 1 and X, and this is 2 and Y. The lower one is inverted scenario. Then you actually, okay. So here, normal scenario, if you look at this here, then your masses can go up forever. It can be very high. But in the inverted scenario, because this small MH cannot exceed 125, and it will bring down all the other masses. So oh, I'm sorry, I can't understand. Yeah. But okay. Then why is that? That's the statistical stability, but let's go for it. And step 2 is this STU parameters. And if you impose it, and this is the RG analysis. RG analysis means that, all the couplings in the particle physics, they they are different. The values are different according to your energy flow scale, right? So, but the problem is the quantum couplings are, how can I say, they are very sensitive. If you run it a little bit, then these are the plots. So this is energy scale. These are quantum couplings lambda 1 to lambda 7 or something like that. Look at this purple one. This is which is lambda 1. Then this is just one example. Then if you increase your energy, then it blows up. Then it will break your perturbativity, unitarity, or vacuum stability, which means that your theory is unstable. So we can say, okay, if your theory breaks, for example, vacuum stability, your theory is done there. That is the cutoff scale, right? So we require that your cutoff scale should be at least 1 TeV. That's step 3. Then collider consists of 2. One is Higgs precision data, and the other is direct search bounds on the BSM Higgs boson, right? So we used the most updated result, and we used the public codes called Higgs signals and Higgs bounds, and that's it. And this is the kind of summary plot I'll show you. So here, I present the survival probabilities, which means that the reference is the parameters that pass step 1, theory and efficiency. And actually, to my students, they obtained 10 million points that pass step 1. About that, we calculate the survival probability. They are very, very interesting. So for example, in normal scenario, step 1, 2, X, Y, PDG, CDF, PDG, CDF, something like that. So we consider 16 different cases. And if you look at this one, PDG has larger survival probability, which means that, how can I say, the CDF W boson mass is a little bit more difficult, but it's okay. Survival probability itself doesn't tell the validity of your model. So I think this is okay. Yeah. But this is serious. For the inverted scenario case, actually type 2 and type Y, they are excluded by this cutoff scale. This is the most crucial one. I'll show you why. So let's discuss which step removes which parameter region. Okay. So this is the normal case, normal scenario case, type 1. Okay, type 1. The upper panels are PDG case and lower panels are CDF case. And this is STU parameter. You have seen this. We have this line. So actually, how can I say? But if you impose this RGE case, yeah. So actually, in Korea, we have this special word. How can I say? 희망고문, which means that hope torture. There is a song named Hope Torture. And so you torture your, friends or actually your lover by hope. I don't love you, but in the future, maybe I may, something like that. That's kind of a song. But I think this situation is like hope torture. If the LHC experiment didn't see anything, then we theorists say, okay, they are just a little bit heavier, try a little bit more, then you can see it, because this line goes forever, right? That's the case for PDG case. But CDF W boson mass clears that hole. I like this guy. But if you look at this one, if you impose this this ST parameter, you have this very heavy mass here, a little point here. But if you impose this RG, your cutoff should be larger than 1 TeV, then all the parameter region is gone. Actually, we generated more and more points here, and we checked that. Yeah. Why is that? As I showed, if you have two large lambdas, then our party couplings, then they will blow up easily. But if you have this, if you have delicate mass difference, then you can have this easily blow up situation. And if you look at this collider case, then it means in terms of this upper bounds, the collider data didn't affect much. Okay. What about this type 2 case? Type 2 case, upper is PDG, lower is CDF, and actually this is RGE. Your cutoff scale should be larger than 1 TB, that condition, but this RGE has, I think, a meaningful constraint on even for PDG because it removes these lines, right? Right? But of course, the most important one, if your our W boson mass is the CDF value, then all the heavy part, they are gone. Which means that their cutoff scale is too low, below 1 TB. Yeah. Yeah. Okay. And what about the difference between type 1 and X? Here? You mean here? Which means that they have a little sizable mass difference, right? So which means they have a little bit larger party couplings. So if you run them, they blow up. Yeah, that's the case. Yeah. And this is the difference between type 1 and X. Overall, they look similar, but in detail, they are different. For example, this is the pseudo-scalar boson mass versus heavy Higgs boson mass with the color code of charged Higgs boson mass. Yeah. Above 1 TB, just above. So if your cutoff scale is below 1 TB, I removed it, that parameter. I have only 10 minutes. When I talk about this muon G-2, I'll tell you detail about these cutoff scales. But for this work, we just imposed one condition. The cutoff scale should be larger than 1 TB. Okay? So, and I think, actually, this is also very interesting because this is a type X in normal scenario. If you look at this tangent beta versus pseudo-scalar mass with color code of charged Higgs boson mass, then there is how can I say this empty space around this pseudo-scalar mass 200 GB. Actually, as I told you, the final constraint is from direct search bound from mostly LHC. And experimental people actually tried very hard to search for new physics signal. And this top decay into charged Higgs boson B, tau nu B, or di-tau lepton signal, or A to GH. This is also very important. The combination of these, they removed this point. So I think the model is very constrained by this CDF anomaly and this very updated, LH searches. So we have to encourage the experiment to dig further and further. Yeah. So that's one thing. And I think I found this is also interesting. This is type 1 and type X difference. This x-axis is the tangent beta, and this is a magnitude of sine beta minus alpha. In type X, you have this, bulk which there is no tendency, just, Higgs alignment should be there nearly. But for type X, it's very interesting. So PDG case, you have some kind of two regions, but in CDF case, they are very, they are quite separated. Why is that? This is type 1, this is type X case, tangent beta versus sine beta minus alpha. I'm sorry, we took the positive cosine beta minus alpha scheme here. So that's why your sine beta minus alpha can be negative here. So here, gray points are after RG case. So you have type 1, type X, you have a similar plot, right? But yellow points are from Higgs signal, Higgs precision data. So in the type 1, you have, sounds reasonable, but in type X, you can see very interesting, separated this, how can I shape, like banana shape, right? Banana shape. So what is that? That corresponds to the wrong sign tau Yugawa coupling. So your tau Yugawa coupling sign is opposite to the, Higgs gauge boson coupling. So I think this is very interesting. Why is that? Because in type X, your tau Yugawa coupling has minus and here tangent beta enhancement. So even though this sine beta minus alpha is near 1, your large tangent beta can flip the sign. So this is also interesting. And what about the inverted scenario? Inverted scenario, as I told you, type 2 and type Y, they are completely excluded. I think this is an important consequence. In type 1, in this case, it's already very low masses. That's why RGE didn't play a significant role. So here you have, this is type 1, this is type X, RGE are okay, but Higgs signal removes, large parameter space. But if you look at this one, I'm sorry, I forgot to say, this is pseudoscalar mass versus this is light Higgs boson mass, and this type, in the case of type X, and very light Higgs mass region is removed. And if you go to the further Higgs bound, then you can remove some parameter points. That's one thing. And this is tangent beta versus sine beta minus alpha, that you can see another wrong sign tau Yugawa coupling. Yeah. What about the other anomaly? We have this muon G minus 2 anomaly, 4.2 sigma. So actually, our group studied, last year, our group studied this muon G minus 2 with Adil. Yeah, at the time we studied type X. But at the time, we wanted to simplify the model, so we took the Higgs alignment limit. And we studied it. We found the nice parameter space, which explains all the theoretical and experimental data. And at the last moment, we applied this so-called lepton flavor universality data in tau and z decay, which consists of tau decay observables, Michel parameters, and leptonic decay observables. And we found that the model is not consistent. So in the global P, standard model p-value is just 0.003, but this aligned, Higgs alignment type X, the largest p-value is only 0.02, which is not so good. Why is that? That's because of this exotic Higgs decay into pseudoscalar pair. That was the problem. So if you exclude this one, this is a tangent beta versus a pseudoscalar mass, then it removes this triangle. That means your tangent beta is too large, about 100. Then this is the key parameter in the lepton flavor data, delta 3, which is proportional to tangent beta squared. So tangent beta is too large, delta 3 is too large, your model is invalid. That was the problem. So this time, we took this Higgs-phobic A, which means that your vertex of Higgs pseudoscalar vanishes. Yeah. Then it will prevent Higgs decay into pseudoscalar pair. In addition, Higgs decay into A and A star decays. So this is very useful. And this Higgs-phobic A determines your sine beta minus alpha in terms of tangent beta and the other mass parameters. So, okay, because I have only 4 minutes, I'll skip most part. And here we imposed this theoretical and experimental constraint similarly, and the survival probability at the end, it was about 0.1% level. Yeah. So so this is the result. This is charged explosion versus pseudoscalar mass with this big MH. Here we consider the normal scenario only. Then these upper panels are PDG, lower panels are CDF. Then actually, at this level, okay, they look a little bit different. at the collider level, they look a little bit different, but this lepton flavor data were so crucial. It removes all the parameters for this light pseudoscalar mass. Why is that? Yeah, global fit to muon G minus 2 plus lepton flavor data, which means that because your pseudoscalar is a little bit heavy, your tandem beta goes up, so which will kill your, the delta tree parameter. So, but actually, there are several interesting points. One common feature is, as before, there exist upper bounds on BSM Higgs boson masses, something like 600 GeV. And the other common part is this one, but I'll skip on. Yeah. But so these regions are removed. But there is a very interesting difference. So you can see this, how can I say, island region. Yeah, in the PDG case. So before the CDF W motion, W mass measurement, you have this very small area, which means that the masses are all around 100 GeV, so they are degenerate. This region is possible. Yeah, I skipped this one. Why is that? Because in the lepton flavor universality data, another key parameter is this so-called epsilon tree. Epsilon tree has two factors, delta 3 times and this combination. And if your delta tree, becomes exactly same or roughly same, then you can reduce this epsilon tree. Then you can reduce chi-scale value. That corresponds to this, this small island here. So I'll tell you this one. I'll skip to RG part because that's one of the most important part. And this is interesting. This is the so-called, I'm sorry, I forgot your name. This is the distribution of cutoff scale. Before, I just imposed your cutoff scale should be larger than 1 TB. But here, we calculated the cutoff scale of all the parameters, and we presented the distributions of the cutoff scale. At step 3 with the collider data, even though we take this CDF W mass, then distribution of cutoff scale looks like this. So here, your cutoff scale can reach about 10 to 7 GeV. And of course, the rate comes down. But if you impose the CDF W mass with this lepton flavor data, it goes quick, something like that, falls down at just 10 to 5 GeV, which means that just 100 TeV. What does this mean? I think this means that if you accept two anomalies at the same time, then, and if you accept the two-Higgs-doublet model or something like that, only type X, then this model cannot live long. We need something new, just really around the corner. That's one thing. And I think I'd like to flash this. I have only 1 second. So this is a PDG case, and this is a CDF case, and this is the allowed parameter points of tragic boson, pseudoscalar boson, and color code means your cutoff scale. And as you can see, the before CDF case, the model was more stable up to higher energy scale. You can see red points like 10 to 7 GeV cutoff scale here or here. But if you impose this CDF W boson mass, the model will die soon. And we studied the other case, and I think we found that here, this is 4-tau WW or 4-tau GW. In CDF case, they have sizable cross-section, but another good news is that, I forgot. I forgot the RG plot. So another good news is that if your cutoff scale is larger, like 100 TeV or something like that, your cross-section becomes higher. So that's another good point. So let me conclude. So I don't know whether this CDF W boson mass is right or wrong, but I hope it is right. Then we have a very exciting situation. Even though you have a new physics model, I think we will have layers of new physics. And I think the first layer can be two-Higgs-doublet. That's it. Thank you.
Okay. Thank you very much. So, any question? Comment? From the
Basically, why in the G minus 2 anomaly you have combined two measurements so to increase the sigma, but in the MW measurements you did not do any combination of the measurements. You took only Tevatron, only CDF.
I'm sorry, I can't understand your question. So when I consider the G minus 2,
The two different measurements of the G minus 2,
two different measurements of
they
G minus
combine them.
two different. What are the two different measurements?
Yeah, the fibrofavalence.
No.
Yeah.
G minus 2, they combined. I see your point.
And in the
So
end
for the
of,
G minus 2, they combined the fermion measurement and Brookhaven measurement.
yeah.
But why didn't I combine?
What I mean.
Because I'll answer that in the next paper. I'll answer the next paper. Yeah, that's my key question. After 3 months. Can we do it in 3 months? Yeah, that's a very good question. Yeah, I'm thinking about it. So the question is, when we consider G minus 2, usually we combine, Brookhaven measurement and formula measurement. That's right. But for the W boson mass, can we combine Atlas measurement and CDF measurement? My answer is no. Any other question?
question from the audience in June? Any other question? I think no. So, let's thank the speaker again. Thank you.